Hey, welcome back. So in the last video, we looked at the dipole moments, and we looked to decide if a molecule is polar or non-polar. So now we're going to look at that dipole-dipole interaction. So anytime you got a polar molecule, right, a molecule that has an overall dipole moment, you're going to have this interaction. So let's go ahead and get started. So let's take a small molecule like hydrogen chloride, let's say. And there's the Lewis structure, although the lone pairs really aren't going to affect us yet. We know that chlorine is more electronegative than hydrogen, so chlorine's electronegativity, I think, is 3, and hydrogen is 2.1. So chlorine pulls electrons towards it, and so that's going to lead to a dipole moment. So it's a bond dipole and it's a molecular dipole. And what's going to happen is that other HCl molecules are going to go ahead and are going to kind of align themselves in some kind of rough and ready way so that the positive and negative ends of those dipoles align. So we can kind of draw those arrows in if you like, and I've drawn it a little bit higgledy-piggledy here. And I can draw kind of a dotted line here, and I'm just kind of representing the attraction between the negative end of that dipole moment and the positive end of that dipole moment. So that would be the dipole-dipole interaction, right? So that is the dipole-dipole, if you like, IMF. Do you remember what IMF stands for? Yeah, it's not International Monetary Fund, it is intermolecular force. So I can go ahead and I can draw these in, and I normally draw them in red, to be honest, but I guess it would be confusing to draw the dipole moment in the same color as the intermolecular force. So that holds them together, kind of like a spider web. So they kind of stick together, and it just causes them to attract to one another. So if we take a molecule like CH2O, and we draw it out, and I draw out the Lewis structure, and I kind of in my head on the fly draw the shape of the molecule. So oops, that should be a hydrogen. So there we go. So we got that trigonal planar arrangement around the carbon, that sp2 hybridization, right? So that approximately 120-degree angle. If we look at this molecule, we can see it's kind of a large molecule. So we need to start off by considering, is it polar or is it non-polar? So maybe you can pause the video and have a go. All right, unpulls it. So what do we do here? We got carbon is bonded to 3 different things. We know that hydrogen's electronegativity is 2.1. We know that carbon is 2.5. So carbon is ever so slightly more electronegative than hydrogen. So I'm going to draw a very, very wimpy dipole moment there. So it's going to be about 0.4 dBi, or a very, very small dipole moment anyway. Very roughly, we measure the dipole moment in units of dBi, and it's approximately equal to the regular electronegativity difference. Carbon is 2.5, oxygen is 3.5, so oxygen is way more electronegative than carbon, so it's going to pull electrons with a very strong bond dipole that looks something like that. And so we have to add those 3 together. So we can kind of start off by saying, well, that's not too bad. We can take maybe the one dipole and the other dipole and the third dipole, and we can look at something like that, right? And we can also look at that and say, well, look, those first 2 dipoles are so wimpy, we can pretty much ignore them. In fact, we can just go ahead and look at the CO dipole moment. In fact, oftentimes, if you take organic chemistry, oftentimes you will just be told to remember that the carbon-hydrogen bond is non-polar, which is not to say it isn't polar. It is like getting a 2 cent a year raise. You know, it's very, very tiny. So for all intents and purposes, we ignore it. So now you got a molecule like CH2O, which is formaldehyde. And of course, formaldehyde has that dipole moment. And so we can go ahead and we can ask ourselves, if you are a molecule of formaldehyde, what would you like to do? And the answer is you would really love to attract another molecule of formaldehyde. In fact, you'd love to attract it using these dipole-dipole interactions, which I'm going to write in that blue dot. So that is dipole-dipole intermolecular forces, and they just kind of pile one on top of the other. So why is it one on top of the other? Well, those dipole moments, right? Those molecular dipole moments line up positive next to negative like so. So formaldehyde sticks together pretty well in solution. So you should ask yourself, in terms of a boiling point, if it has a dipole-dipole interaction, is that going to raise or lower the boiling point? The answer is it will raise it. So if the molecules stick together more easily, right, or more readily, I should say, then they're going to have a harder job to be boiled. And when we boil, remember, we break those intermolecular forces. So we're going to have to put in energy. We're going to have to boil it. by raising it to a much higher temperature. So the boiling point would be elevated. So if we had a switch where we could turn on or off these interactions, anytime we turn them on, the molecules stick together more readily, so we have to boil at a higher temperature to get it to boil regularly. All right, good job.